Hey guys, this is Mr. Mitchell. Today we're going to be looking into energy diagrams. So we can start this out by talking about energy chains. We started off this unit by discussing these ideas of energy chains that help to display the law of conservation of energy because we saw how energy could go from one form to the next, to the next, to the next. We traced the flow of energy through a system. And so maybe we dropped something and it started having GPE and then we let it go and then that turns into KE as the object falls. Well, that's all well and good, but an energy chain doesn't really communicate to me the amount of energy at all. And so that's where this idea of energy diagrams come in. An energy diagram, instead of being limited to just seeing the types of energy that you have at certain points and then the transformations that happen between those types, instead of that, what an energy diagram is going to do for me is it displays both the forms of energy, so we still see, it has KE or it has thermal energy or it has GPE, but it also displays the relative amount of energy at a particular point in the energy chain. And so these are really valuable because now we can start to distinguish how much of each type there is. So this is the example scenario. It's the same one that we've had illustrated in the past couple of slides. A car transforms the chemical potential energy that it has stored in gasoline into kinetic energy when the car moves. When the car begins to skid to a stop, its kinetic energy is then transformed into thermal or heat energy in the road, the tires, and the brakes. So we're going to look at a couple examples of energy diagrams that'll explain more specifically this transition right here, the kinetic energy going into thermal energy, or as you saw kind of illustrated before, these are all going to be diagrams for that illustration we saw in the beginning. So the first type of energy diagram that we'll come across is a text variation. So what we do in this circumstance is we manipulate the font size, and so you see that the font size is different for each of these things, all right, to show the relative amount of energy. So we start off, right, in our scenario with a really large amount of kinetic energy. It's real big. And when we have that big amount of KE, the heat energy is really negligible. There's not a whole lot of it going on. And so the heat energy is shown as really small. As we go down the line, right, the car is skidding to a stop. So it's slowing down, slowing down, slowing down, slowing down. And so ultimately we end up with a real small amount of KE because the car's not really moving anymore. It's slowing down. It's not going to be going as fast. Well, what happens when it slows down and the KE goes down? All that energy is transformed into heat energy or thermal energy. And so at the end, even though it's going really slow and has a small amount of KE, what happened to all that energy? Well, it got transformed into heat energy, and so the amount of heat energy goes up. So we see, based upon the size of the text, how much of each type of energy there is. If there's a real big text, then that's a lot of that type of energy, and if it's a real small text, it's not so much of that. The second energy diagram we're going to look at is just a side-by-side bar graph. So you kind of take a bar graph and then you build another bar graph with it. So the light color purple here is representing kinetic energy, and then the darker pink color is heat energy. And so we see that if I'm just looking at the purples, we start out with a lot of kinetic energy up here, and then as we go along, the kinetic energy decreases, it decreases, 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 decreases. And then what happens to the heat energy? Well, if the kinetic energy is going down, and we know that energy is conserved, right, so it can't be created or destroyed, it's got to go somewhere. Well, it's turning into heat energy, and the heat energy is going up. So as the kinetic is going down, the heat energy is going up. This is a side-by-side bar graph because we see both of them represented for any scenario at the same place. So in this first, 1 second time interval, it's a lot of kinetic energy and a little bit of heat energy. At 2 seconds, it's a little bit less kinetic energy, and we see that the heat energy is going up. 3 seconds, we see that kind of balancing out a little bit more. By 4 seconds, it's even. They're both the same. And so the same process kind of goes along. The third kind is another type of bar graph, but it's called a composite bar graph because what we do is we actually combine those two bars into one bar together. And so what happens here is it makes it a little bit easier to see the law of conservation of energy, which we're going to talk about in a second. But instead of having two bars side by side, now they compose one bar. And what do you notice about the size of the bar? Well, the size of the bar is always exactly the same. They all are at the same height. The reason for that is that the energy didn't really go anywhere, right? It's just transforming to another type. It can't disappear. And so we start off with a real big bar of kinetic energy and a real tiny piece that's representing the heat energy. And then as the car slows down, that kinetic energy goes down, but what happens to the heat energy? Well, the heat energy is actually increasing. We see a large amount of heat energy on top. Okay. The last one is a pie chart. We actually should have seen this one when we did our energy skate park diagram. So if you saw your little energy skate park guy and you turned that pie chart on, that's representing a energy diagram. And so the pie chart is nice because, again, you're kind of seeing parts of a whole. Remember that the total amount of energy can't change. And so instead of saying like, oh, I'm going to have, this size bar and then this size bar and then this size bar, it almost looks like the energy changes. Whereas the pie chart allows you to see, okay, well, this is the total amount of energy that I have. And in this interval, only this tiny little portion of it is actually heat energy. And the rest of it is all kinetic energy at this point. At interval 4, now we're at the kind of the halfway mark. So we have half kinetic energy and half heat energy. And then that continues all the way down to interval 7. Well, now the kinetic energy is really small and the heat is very large. So again, this is almost like the composite bar graph where it helps you see the law of conservation because the circle is the same size every time. It's representing the same exact amount of energy. It's just telling me how much of it is kinetic and how much of it is heat. So as far as the law of conservation of energy goes, it's integrated into these very well. We sort of briefly mentioned it when we talked about this composite bar graph down here. We said the law of conservation of energy tells us energy can't be created and energy can't be destroyed. So the total amount of energy in this system still needs to stay the same, even though it's changing forms. So when we look at a composite bar graph, we see that all those bars are the same height, and so they're representing the same amount of energy. It's probably about 28 joules of energy right there. So, and then we move on to interval 2, still 28 joules, 28, 28, 28, 28, right? So they're all the same amount of energy. It's just telling me, okay, well, at this point, it's a lot of kinetic, and at this point, it's a little bit less and a little bit less, and by the end, it's almost all heat energy. Same concept is shown in our pie chart, right? Again, the circle is the same size each time, and so we're just seeing that even though it's the same amount of energy, the types of energy, at least the ratio between them, is changing. So in this case, the first one, we have a little bit of heat energy, then we have a little bit more, and then by the end, it's almost all heat energy. You can kind of see it in our side-by-side bar graph and in the text version, but it's a little bit less obvious, right? If I were to take these two columns and add them together, then I would get that same 28 joules of energy. If I were to take these two columns and add them together, I get that same 28 joules of energy. And so you can kind of see, if you kind of put things together there, that it would be the same amount of energy. And then the same deal with the text version. If I took these two and maybe put a number to them and added them together, we'd see that it's about the size, a certain size. And then as I kind of crunch one down and the other gets larger, we're still kind of balancing that amount of energy out. So that's all we have on energy diagrams. They're pretty straightforward, builds off of our concept of energy chains, and hopefully this is helpful in at least seeing how the law of conservation of energy is applied to these guys.